Lesson 19 is about different areas within circles, and in 19.1 we're just going to get into the area formula for a circle. We're actually going to derive it from the parallelogram area formula. So area of a parallelogram is area equals base times height. And that's because you can pretty much rework any parallelogram into a rectangle, and in a rectangle it's base times height or length times width as well, because you can just kind of take the amount of units across the bottom of a rectangle and multiply it by the amount of units across the side of the rectangle, and that'll give you the total amount of square units within the rectangle. So the reason that we can kind of rework a parallelogram into a rectangle is because if I just cut off this slice down here, let's say I slide it over to the other side, then all of a sudden I have 4 right angles all across it. This part would be gone, and then I have what is a rectangle now. So that's that figure in the middle. And then with a rectangle, for trying to find the area, we can just pretty much fill it with a bunch of square units, which is what happens on the far right side. And that's what area is just how many square units can we fit within something. So across the bottom, if we count up the amount of square units, that's going to give us the base B. And then across the side, if we count how many square units are from top to bottom, that's going to give us the height H. You can technically count all the square units, but that would take a really long time. So instead of counting, we just multiply how many there are from side to side, and then by how many there are top to bottom, base times height, and that'll give us the total amount of square units within that figure. So we're going to kind of take that formula, that principle, and apply it to circles. But if you're like, okay, well, circles are not shaped like rectangles, we can rework them to be pretty close to at least a parallelogram. I know you can kind of see the figures down here. We'll talk about how we're getting from start to finish on this circle, and then transition into finding the formula. Okay, so in our first circle, we of course have just a regular circle, and if we cut it into 4 even parts, or 4 equal parts, like fourths, and kind of rearrange them like this, where they're alternating, one is pointing up, one is pointing down, we get this second figure. So slice 3 would go right here, and then the 4th slice would finish off over here. And then, of course, that figure in the middle, it doesn't really look like a parallelogram. I feel like it looks kind of like a worm. But we can keep cutting each of our slices into smaller slices, into halves. And honestly, the more times you do it, the more it's going to resemble a parallelogram. So, for example, if I take the green slice and cut it in half, and then kind of switch the way they're positioned, that would end up being these 2 slices right here. Normally, of course, we would just kind of actually do this with paper and scissors and stuff, but we don't really have that option, so we'll draw it here. So if I take that blue slice and I cut it in half, it becomes these next 2 slices. If I take the purple one and cut it in half, it becomes these 2. And then if I take the pink one and cut it in half, it becomes those last 2. And you can already see just by cutting between the second figure and the third figure, it's starting to resemble a parallelogram more. And the more times that you cut each slice into half, there's no limit how many times you can do it. We're going to stop here, but there's no limit technically. You could continue to cut them in half, and it would just look more and more and more like a parallelogram. And so that's why we're able to use the area formula for a parallelogram to derive the area formula for a circle. Okay, so now if we kind of want to piece together what each of the what the base and the height of our new kind of circle parallelogram would be, we need to refer back to the first picture of the circle. So if I look at let's say this portion right here of the circle, so from the point of that slice to the outside of the circle, that's the radius. And I can draw that into my new figure. So if I start at a point and go to the outside of the circle, which is all the curved edges, that's my radius. So we'll label that with R. And then all of the curved edges added together is the circumference. So this plus this plus this plus this would be the circumference. Or if we go on the third figure, all of the curved edges on the top and the bottom would end up being the circumference. If we're using the area formula for a parallelogram, we just need the base though. And so since if you combine all the curved edges, you get the circumference. If you just take half of them, like just across this, not across, but just half of the circumference, it would just be like 1/2 times the circumference. Sorry, I was kind of saying that weird, but 1/2 times the circumference. And the reason you don't have to do the full circumference is because, hold on, I'm going to spell that wrong. I'm still not confident for some reason. Okay, so sorry, multitasking. So the reason that you don't have to do the full circumference for the base is because the base only goes like from one side to the other, and the circumference would be like all the way around, all of the curved edges combined. Okay, so that's enough to kind of put together our formula now, base times height. So it'll be area equals base, which is 1/2, times the circumference, and then times the height, which is the radius. I'm just going to leave it as r. And then we know what the formula is for circumference, so we can go ahead and put that in. So it's 1/2 times circumference is, since we already have an r in there, I'm going to use the 2 pi r, not the pi times diameter, since we already have the radius in there, so it'll make it a little bit easier to combine than radius and diameter. And then now we can simplify. So 1/2 times 2 is just 1. So those kind of like almost cancel each other out. They would just be 1, so we don't need to write it. And then we have a equals, I'm going to bring down that pi. And then if I multiply r times r, that's r squared. So pi r squared, and that's as like simplified as I can get it. And that's the area formula for a circle. So area of a circle, the area of a circle with a radius of r is area equals pi r squared. Okay, moving down to 19.2. A sector is a figure in a circle that is bounded by a central angle and the intercepted arc of the circle. So I like to think of like a sector as like a slice of pizza. The arc is the crust. So the arc is just like kind of the outside part, the circumference like portion of it. The sector is the entire slice. So in this figure, you can see the sector is in red. Or the region in circle C that's enclosed by angle ACB, so that's this angle right here. And arc AB, this arc right here, is a sector of circle C. Okay, so sector, think of, anytime you see sector, think of like the full slice of the pizza. Moving down to finding the area of a sector. So a sector is a fraction of the interior of the circle. Therefore, we can find the area of the sector by multiplying the fraction that it represents by the area of the circle. So the area of a sector is very similar to arc length. With arc length, we had to find the fraction out of the whole circle and multiply it by the circumference to figure out what portion of the circumference the arc length represented. With sectors, we're dealing with a like kind of whole slice, including like the area. So we're taking the fraction out of the whole circle and multiplying it by the entire area of the circle. So think like if I had a sector that was like 1/3 of the circle, I would do 1/3 times the entire area of the circle to find the area of just the sector. So we can set up our formula by area of the sector is equal to the fraction, like how big is the slice out of the whole, times the area of the entire circle. And then we know the formula for the area of a circle is pi r squared, so we can go ahead and put that in for area of the circle. So we'll say area of a circle equals fraction, again, how big is our slice, times pi r squared. And then that kind of leads us into our like more formal definition. So area of a sector. The area of a sector enclosed by a central angle whose measure theta is given in degrees is area equals theta over 360 degrees times pi r squared. So this symbol right here is a Greek letter that we use to represent angles. Typically, it's called theta, Theta. And so when our central angle theta is given in degrees, we can use this formula to find the area of a sector. So it's the central angle over 360 times pi r squared. Okay, example 1, find the area of a sector. So using the formula A equals theta over 360 times pi r squared, we just have to identify each individual part and go ahead and substitute it into the formula. So theta, that's our central angle. The central angle is the angle that kind of helps create that sector, and so that's 120 degrees. So we would start with 120 degrees over 360 degrees, and then times pi, which is just the numbers, we leave it as is, and then r squared, which our radius is 3/2. So pi times 3/2 squared. And then I'm just going to go ahead and put 3/2 in parentheses just to remind us to square kind of both parts. So pi times 3/2 squared. We have a kind of a lot to simplify for this one, so we'll start with reducing the 120 over 360. We can divide those both by 120. So if we divide both by 120, 120 divided by 120 is just 1. 360 divided by 120 is 3, and then the degree symbols would also cancel out. And then I'm going to just leave the pi right there for right now, and then times r squared, so it's 3/2 squared. I know we can change 3/2 to a decimal, but like some of the multiple choice options will have the answers still in fraction form, so you just kind of want to leave it there as long as you possibly can. But the way that you square fractions is you just have to square numerator and denominator. So you would do 3 squared, which is 3 times 3, so 9. And then in the denominator, you would do 2 squared, so 2 times 2 is 4. And then now we have a few different, well, we can think of this as pi over 1 if it makes it a little bit easier to see them all as fractions. We can multiply straight across and then reduce, or you can cross cancel. And in order to cross cancel, as long as all 3 fractions are being multiplied, they don't have to be next to each other to cross cancel. So what I mean by that is like 9 and 3. One is in the numerator and one is in the denominator, and as long as all the fractions are being multiplied, that's really the only criteria that we have to follow, is one is on up top, one is on bottom. So those we can cross cancel. If we divide 3 by 3, that becomes 1. 9 divided by 3 becomes 3. And then now nothing else to cross cancel, so we can go ahead and multiply straight across. So left over, I have a 1 times pi times 3, so that would be 3 pi. And then in the denominator, I have 1 times 4, so that would be 4. So 3 pi over 4. And this is inches for our radius, so it'll be inches squared for our area. And then I want to go back up to the previous step and just kind of show you what it might look like if you wanted to multiply straight across and then reduce after. So if the cross-canceling thing was like just, no, didn't work, didn't click. And you don't have to ever cross-cancel. You can always just kind of multiply and then reduce at the end. So for multiplying straight across, it'd be, I'm going to do that part right here. 1 times pi times 9, so it'd be 9 pi. And then in the denominator, it'd be 3 times 1 times 4, so it'd be 12. And then now 9 and 12 both have a common factor of 3, so I can divide both by 3 to reduce. So 9 divided by 3 is 3, and then the pi tags on. And then 12 divided by 3 is 4. So we end up with 3 pi over 4. It's the same answer. That's why it really doesn't matter if you cross cancel or you reduce at the end. It really just comes down to personal preference. So we end up with 3 pi over 4 square inches. And then if we wanted to convert it to a decimal, or if you had to get like a decimal approximation, the way you would do it is you would just do 3 times 3.14 for pi, and then over 4. So you just multiply 3 times 3.14, or if you have the pi function on your calculator, you can also use that. So 3 times 3.14 is 9.42, and then you would divide that by 4, and that ends up being approximately 2.36 square inches. So without pi multiplied in, it'd be 3 pi over 4 square inches. And then if we do multiply pi in, it'd be approximately 2.36 square inches. It's helpful to be able to get to both answers, just kind of depending on what answers are available to you in Canvas.